in real life situations, we often have to deal with more than one variable. As a simple example, suppose you have to study for two tests, a math test and an English test. You have a total of 10 hours to study for both tests, and it's very easy to mathematically model this situation once we learn about the Cartesian coordinate plane. Here's the familiar Cartesian coordinate plane, also known as the Cartesian coordinate system, named after the person who created it, René Descartes. As you know, we basically have two perpendicular real number lines forming the basis of the Cartesian coordinate plane, and what we can do then, using a grid, the intersection points will refer to points of the form P of xy, where the first coordinate is going to be the horizontal component and the second coordinate will be the vertical component, or the y coordinate. Now, once you create a Cartesian coordinate plane, this old number line that we used to know is no longer called the number line, it's called the x-axis. Okay, so you have the positive x-axis here on this side, starting from here and going there, it's that ray, and then you have this ray which represents the negative x-axis. Then you have the positive y-axis and the negative y-axis. Notice that they are lines, even though we don't see the little arrowheads. So of course, this is just a very small part of an infinite plane, which goes forever in all four of those directions, right? So one thing we note right away is the fact that the two axes of the Cartesian coordinate plane break the plane up into four regions. These regions are called quadrants. So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. As you notice, we go in a counterclockwise manner for our quadrant numbering system. And notice that all the points that are in the first quadrant will have x and y coordinates which are both positive. All the points in the in the second quadrant will have x values that are negative, y values that are positive, right? In the third quadrant, we'll see that any point in this quadrant will have both x and y coordinates negative. And in the fourth quadrant, the x values will be positive, but the y values will be negative. So when you are told, for example, to graph the point -5, 7, you're basically given a set of instructions. What the instructions are is that you start here at the origin, 0, 0, then this is the horizontal instruction and that's the vertical instruction. So from the base, you know, at the origin, you're going to go 5 units to the left, and then you're going to stop and you're going to go 7 units upward, because that's a positive 7, and you end up right there. So -5, 7, the ordered pair -5, 7 corresponds to a single point in the Cartesian coordinate plane. It's not 2 points, it's just a single point. For example, the ordered pair 2, -3 right here is another set of instructions. It's telling you to start at the, you know, base camp at the origin, go 2 units to the right, and then 3 units downward, etc. So you can see that -5, 7 is a second quadrant point, -2, -3 right here, go left 2, down 3, that's a third quadrant point. 2, -3, for instance, is a fourth quadrant point, etc. So if somebody tells you to graph 6, 0, of course that means start here, move 6 units to the right, and stop, because it's 0, the y-coordinate. Don't go up or down. So you're going to end up with a point on the x-axis, in fact on the positive x-axis, right? Notice that if somebody tells you, hey, what quadrant is that point in? Since you don't want there to be a big argument between quadrant 1 and quadrant 4, you say, hey, it doesn't belong to any quadrants. It is a quadrantal point. That's what we call points like that lie on one of the axes, right? We call them quadrantal, like so. Okay, so we say that the ordered pair 6, 0 is a quadrantal point. Same thing would go for 0, 6 up here, and for -6, 0 right there, and 0, -6. So those are 4 examples of quadrantal points. So the Cartesian coordinate plane is a very, very useful tool that we will be visiting for the rest of our mathematical career. Now we can go ahead and start moving toward the graph of our scenario here with the number of study hours. For example, you can let x be the number of hours you will study math, and let y be the number of hours you'll study English. And then we can, of course, form a linear equation in 2 variables because we know that x plus y has to equal 10. That's a constraint that creates that equation for us. Now, one of the ways, for example, you could split the 10 hours between math and English is to let each one have 5, right? That would be if you're about as comfortable with the 2 subjects and you really just want to give them equal time, right? But on the other hand, maybe you are a master of writing and maybe math is not your favorite subject. In that case, you may want to give math more time, maybe 7 hours to math, 3 hours to English. Or, you could, of course, don't have to give whole hours. You could do partial hours as well, right? 2.5 hours to one, 7.5 to the other, etc. All depending on how much you feel that you need to study for either one. Notice that there's a continuum of possible values for x and a continuum of possible values for y. We're going to make a table of values just based on some real simple, nice points. We'll use whole numbers, but do realize that that restriction is just self-imposed. We don't have to pick such perfect numbers. We can obtain a nice graph of our situation with the number of hours available for math and English by plotting points that satisfy this equation on the Cartesian coordinate plane. Notice that the 2 extremes that the values are going to fall within are 0, 10, which corresponds to studying 0 hours for mathematics and 10 hours for English, and 10, 0, which is on the other end of the spectrum, where you spend 10 hours on mathematics and 0 hours on English, as you can see here between 0, 10 and 10, 0. Now, this equation in itself is capable of any kind of solution, even with ones where, for example, the y may be negative, or some over here where the x values may be negative, right? But because of the constraints of this real life situation, all the values that are going to be possible for this particular scenario are going to fall somewhere in this zone right here, correct? And do notice how they all line up so nicely. That is not at all accidental. That's precisely why this kind of an equation, which we'll find has a very specific form, is called a linear equation. As far as these ordered pairs are concerned, here's, for example, 5, 5, which we mentioned earlier. That's when you allow 5 hours for math and 5 hours for English, etc. And then you can go toward one or the other spectrum, depending on how comfortable you are with one of the subjects. If you notice, we have solved this equation for y to get y equals 10 minus x, because that makes it really easy for us to obtain y values if we use a specific x value. And for example, when x is 1, y is going to be 10 minus 1, which is 9. When x is 6, for example, y is going to be 10 minus 6, which is 4, etc. Now, these are just some very, very simple choices for x we have made, but notice that there's a continuum of values, as we have set for x, and also a continuum of values possible for y. And just for the sake of simplicity, we have only picked these nice ones. Otherwise, if you really graph all the possibilities, you would perfectly fill in this line, straight line, that would go through all these points. And in this particular instance, we would just get the segment, but if we had no restrictions, then that would continue in both directions, and we would get the entire straight line associated with this linear equation. So that example was just a very intuitive introduction to help us get ready for a formal introduction of linear equations in two variables. Notice that any equation that can be put into the form ax plus by equals c, with a, b, and c just being real numbers, and the restriction that one of them should not be 0. Notice that if they're both 0, that means both our variable terms are gone and we no longer have a viable equation. So the one requirement we have is that either a is not 0 or b is not 0. As long as that happens, we have ourselves a linear equation. And this is called a linear equation in two variables. And we have already seen why it's called linear, because once we graph it using ordered pairs x, y in the Cartesian coordinate system, we end up with a straight line, given that with this kind of an equation, y always varies with respect to x at a constant rate. Now, what makes this really unique is the fact that we can graph them very efficiently, because all we need to get a perfect graph of a straight line is exactly 2 points. This fact is expressed mathematically as 2 distinct points, and here distinct just means different. 2 distinct points in a plane determine a line. That's a very, very strong word when we say determine a line. So what does that mean? That means given 2 distinct points in a plane, there's one and only one unique line that passes through those points. Any other line containing those 2 points would have to overlap with the first such line drawn, right? So for example, if we put 2 points, such as, for example, this point and this point, right, on the plane, then we can get a straight line, draw a straight line that goes through them, such as this one. And what this, let's make those original points a little bit larger. Okay, and what makes this line special is the fact that it is the only unique line that goes through those 2 points. So any other line that would go through those 2 points would basically overlap with this line. That's what this statement is basically saying. So that means all we need to do to find the graph of a line is 2 points. When it comes to understanding lines, the most important quantity is the one that gives us that constant rate of change that we have discussed previously. And that quantity is called the slope of a line. And the way that we define it is by taking 2 points on the line and then trying to find exactly what kind of a vertical change is associated with a given horizontal change. So the vertical change from this elevation to this elevation, that's what we call delta y, and the horizontal change from this location to this location on the horizontal axis is what we call delta x. Now notice that if this is the point x1, p1, x1, y1, then that means this point right here is x1, and this point right here is y1, and for this point p2 of x2, y2, that means this is x2 and this is y2. So this distance here is x2 minus x1, which is of course the same as this distance here, right? And notice that this distance here is y2 minus y1, which of course means it's the same as that distance there. Okay, so when we take the change in y and divide it by the change in x, that's how we found out how y changes as the x values change. So the rate of change of y with respect to x, that's really what the slope is. And we'll see that it tells us a lot about the shape of a line as we move forward. All right, so let's suppose that we want to find the slope of the line going through these 2 points, 3, -6 and 5, -3. Basically, all we need to do is pick one of these ordered pairs to stand for x1, y1, and pick the other one to represent x2, y2. Then we can quickly use the slope formula and calculate it. Now, be very careful, because if this is your y2 and this is your y1, you're going to get -3 minus quantity -6. So you do need the parentheses, and eventually that's going to turn into a plus. So you really want to watch out for that kind of arithmetic detail. And this is of course your x2 and that's your x1, so we get x2 minus x1, we compute that and we get 3/2. So that means every time there's a change of 2 in the horizontal direction, there's going to be a corresponding change of 3 in the vertical direction for this particular line. What is really important to keep in mind here is the fact that it's this ratio that's really critical to us. So for example, any equivalent of that will satisfy this linear situation as well. A real-life application can really help us understand just what we mean when we say that slope stands for rate of change. So a soda can costing $1 in 1980 would have cost about $2.50 in 2020. Find the rate of change of the price of a soda can with respect to time. So in order to accomplish this goal, we'll make a table of values, and we'll let the year kind of represent the X column and the price the Y column, right? So we have 1980 and 2020 for the years, and the price associated with 1980 is $1, and the one associated with 2020 is $2.50. So now we can let the ordered pair 1980, 1 be our X1, Y1, and the ordered pair 2020, $2.50 be our X2, Y2. Now if we apply the slope formula, we end up with Y2 minus Y1 over X2 minus X1, and that gives us 250 minus 1 over 2020 minus 1980, so we get 1.5 over 40, which is basically $0.0375 per year. That's just reducing that using a calculator. If you just divide 1.5 by, let's see, let's clear this. If you divide 1.5 by 40, that's where you get the 0.0375. okay? And if we take that and actually turn it into cents, which will make it kind of a more tangible number for us, we get, by multiplying using this unit factor, because we know 100 cents corresponds to $1, so we end up with 3.75 cents per year. When you multiply by a unit factor, you want to make sure that units are positioned in such a way that they cancel out and leave you the desired units at the end. So basically a Coke of a can of, sorry, biased toward the Coca-Cola, I guess. I must have been a fan, but anyway, the price of a can of soda has gone up. Basically, notice this is a positive rate of change, so it's gone up about 3.75 cents, less than 4 cents per year now, which is an amazingly stable pricing structure. This has been really kept to a minimum of inflation. So there is an example that tells you what we mean by rate of change. Of course, you could do this for, say, the price of an average house, right, in 1980 versus 2020, or whatever other quantity you may be interested in trying to find an average rate of change for. Okay, we'd like to discuss the types of slope now. Notice that when you're looking at a line that goes up, if you're looking from always, when you look at a mathematical graph, you always want to be looking from left to right, right? In other words, if your X values are increasing, what's happening to the Y values? Notice the Y values here would be increasing as well. So this is what is representing a positive slope, and it makes sense from the point of view of the formula as well, because notice if you want to get from this point to this point, you would have to go up and then to the right. So going up, that would correspond to a positive change in the Y direction, and if you're going to the right, that would indicate a positive change in the X direction. So you get positive over positive, which is going to be positive. Now notice that if X values increase but Y values decrease simultaneously. That means to get from one point to another point on this particular line, you would have to go down and then to the right. So the change in y would be negative, whereas the change in x would be positive. So we would get a negative over positive situation, which gives us an overall negative. So this kind of a line has a negative slope. And what about horizontal lines? Well, let's see. When you want to get from one point to another on a horizontal line, notice there is a positive delta x involved, but there is no change in y, right? So your delta y is 0. So the slope is going to be delta y over delta x, which is 0 over positive, so you end up with 0. So this is what holds for all horizontal lines. They're all going to have a 0 slope. Now be very careful. That is very different from saying it has no slope. That's the case with vertical lines, because if you're trying to go from one point to another on a vertical line, there's a positive change in the y direction, but no change in the horizontal x direction. So this time it's delta x, which is 0. So the slope is going to be delta y over delta x. So you're going to have a positive change over 0, which is undefined. So vertical lines have no slope. That's where you use the language no slope. All right, not for these. 0 slope is not the same as no slope. So when there's when it's undefined, that means there's no well-defined number that we can present for the slope. Notice that if you say position yourself on a line like the one over here, you would be going up like that, right? On this one, as x values increase, you would descend, right? On this one, what would happen? You'd just stay at the same elevation. And on this one, you would be in trouble, right? So one of the ways that you can think about when we say no slope is kind of think about it as infinite slope, right? So always keep these 3 or 4 situations in mind when it comes to slopes of lines. All right, here we're asked to find the slope of this line depicted here in red using the slope formula. Remember, to use the slope formula, we need 2 points. So why don't we pick this point and say this point. Okay, they're as good as any. So that would be the point 4, 0 and the point 4, 1, correct? So we get m equals, now I can go ahead and think of this one as x1, y1, and this one as x2, y2. It's arbitrary. You just have to be consistent when you do the subtraction, right? So that's going to be y2 minus y1 over x2 minus x1. So we're going to get 1 minus 0 over 4 minus 4. So we get 1 over 0, and of course you know division by 0 is undefined, so this is undefined. All right, so that's using the slope formula to verify that the slope of a vertical line is undefined. All right, so in this case we're asked to find the slope of the line depicted without using the slope formula. In other words, just trying to understand the slope graphically, right? So when we look at this line, notice if we can find two nice points which are, say, going through corners of these squares, that would be very helpful. I noticed that I can use this point and this point. So the question is, if the only kind of movements available to me are up, down, or left, right, what kind of movement would I need to go from this point to this point? Notice I would have to go down, right? How many units? Well, that's 1, 2, 3 units. So I would get m equals the change in y, which is -3 over, and then notice I would have to go this way to the right, so that's a positive change in the x direction. How many? 4 units over 4. So of course normally we would just put the minus on the side and we would say m equals -3/4, like that. Okay, so there is how you would find the slope of a line graphically. 2 points are of particular interest to us when it comes to trying to graph linear equations, and that is the x-intercept and the y-intercept of a line. Notice that the x-intercept is nothing but the point where the line crosses the x-axis. The y-intercept is nothing but the point that of intersection of the line and the y-axis. Notice that at the x-intercept, right, because it is a point on the x-axis, the y-coordinate is going to be 0. And the opposite is true for the y-intercept, because the y-intercept is a point on the y-axis when the coordinate that's going to be 0 is the x-coordinate, right? So this gives us a hint as to how to find the y-intercept and the x-intercept. In order to find the x-intercept, we just let y be 0 and solve for x. That will give us this value of a. And to get the y-intercept, we let x be 0 and solve for y. That will give us this value of b. Alright, so in this problem, we want to find the x and y-intercept of this particular line. 3x minus 4y equals 12. And we can see that it is in the format for linear equations. So let's go ahead and see how we can do so. So we have 3x minus 4y equals 12. So remember, in order to find the x-intercept, all we have to do is let y be 0 and solve for x. So if y is 0, we get 3x minus 4 times 0 equals 12. And of course, 4 times 0 is just 0, so we get 3x equals 12. So dividing both sides by 3 gives us x equals 4. So the x-intercept is 4, 0. And to get the y-intercept, we basically let x be 0 and solve for y. Alright, so when x is 0, we get 3 times 0 minus 4, y equals 12, and therefore negative 4y equals 12, because remember this part is 0, so we get y equals negative 3. So the y-intercept is 0, -3. So now eventually we'll go ahead and use those 2 points to graph the line. In fact, we could do so right now, nothing holding us from doing that. So let me get a Cartesian coordinate plane ready. Okay, so we're going to go ahead and plot 4, 0. So on the Cartesian coordinate plane that we can see here, we can plot 4, 0 and 0, -3. And now we can just draw the line that goes through those 2 points. There we have it. Okay, so we just made a graph of this particular line using nothing but the 2 intercepts. All right, we should have all the information we need to go ahead and start graphing linear equations. All right, so what you have to keep in mind is that we need only 2 points to graph a line, and that's what brings us to the intercept method, which we already utilized and we're going to formalize now. The easiest way to graph of a line where none of these constants is 0 is by finding the 2 intercepts. Something interesting happens if any of those constants are 0. Okay, so we'll get into those special cases, but with many equations like this one, which we just worked out, the constants are not 0, and we can easily obtain both an x-intercept right here and a y-intercept. So basically we quickly get a graph of a line like this with all the constants non-zero by just simply letting x be 0 and finding y to get the y-intercept, and then letting y be 0 and solving for x to get the x-intercept and getting our graph. This is called the intercept method. Works really well when none of the constants are 0. With the cases where the linear equation is given in a format which is either solved for y in terms of x or for x in terms of y, the intercept method may not be the easiest approach. The easier way method may be just substituting values for this variable, which is being used to solve for the other variable, and then obtaining values for the variable for which the equation is solved. For example, here I would give x a couple of values, and remember, this is completely random. You could use any points you wanted here, but we might as well stick to the easiest ones for calculation purposes. So we'll go ahead and use 0 and 1, and we'll obtain -4 when x is 0. We get 0 minus 4 is -4. When it's 1, we get 3 minus 4, which is -1. And then we go ahead and graph our line here. Notice that if you were to try to use the intercept method and you let the y value be 0, you would have ended up solving this and getting a decimal point like this, or a fractional value, whereas doing it in using this method, we didn't end up having to deal with any decimals or fractions. Same thing here. I would just give y a couple of different values. Since x is solved in terms of y, first we give y a couple of values and we quickly solve for x. So we get these results here and we graph it. Again, if we were to try to do this one using the intercept method as well, we would have had to deal with a point which has fractional or decimal coordinates, and we avoided that by using this method instead. And this works really well when the equation is solved either for y or for x. As I mentioned earlier, something really interesting happens when any of these constants is 0. We'll start with the case where C is 0. When that happens and A and B are not 0, we end up with oblique lines. Well, oblique means neither horizontal nor vertical. So we end up with oblique lines that actually cross the origin, which is 0, 0. So here's an equation of that form where C is 0. Notice with these, the intercept method is not going to work as far as graph is concerned, because the x and y intercepts of these lines are the same point, namely the origin. So trying to use the intercept method will only get you 1 point. So at that point, you're going to need to get one other point, because remember, you only need 2 points to graph a line, right? So here's what we'll do. We'll go ahead and take the equation and we'll solve it for one of the variables. In this case, I've solved it for y. So we get 2y equals negative 3x, so y equals negative 3/2 x. And now we have the equation solved in terms of one of the variables. So all we do is give x a certain value and find the corresponding y value. Now here's where we can get a little clever, because if I use 1 here for x, I would end up with a fraction. Of course, we're not afraid of fractions, but if we can avoid them, we will, if it's easy to avoid them. I noticed that if instead of using 1, I were to use a 2, then I would easily avoid having to deal with fractions. And when I plug in a 2 here, the 2's will cancel out. I get negative 3 for y, and I can easily graph my line using the 2 points that I have obtained. A lot of times it's good to get a third point just for safety, in case you made some kind of an arithmetic error. So whenever time permits, try to use 3 points. But if you're super careful, 2 points is really all you need. All right, the other cases where something interesting happens are the cases of horizontal and vertical lines. For those, either A or B is going to be 0. And we're going to go ahead and look at some examples which will tell us which one is which. And the classic approach of, say, the intercept method and all that is not going to work for these. You have to just understand the Cartesian coordinate system really well, and will reason how these will have to be graphed very easily in that case. All right, so here we want to graph 2 equations, x equals 2, y equals 2. Notice both of these can be put in the form of ax plus by equals c, so they are both linear equations. Let me show you, for example, for this one, you have 1x plus 0y equals 2. For this one, you have 0x plus 1y equals 2. Just in case you were wondering how these can fit into the mold, here's the way they do it. So notice that for this one, A is 1, B is 0, and C is 2. So this is the case of B being 0 in ax plus by equals c, and this is the case of A being 0. And notice the way we graph these is when you have x equals 2 and there's no y in the equation, that means the values of x don't depend on the values of y. Here, x is always going to be 2. So all you have to do is go ahead and pick a few points with y, different values for y, knowing that the x value isn't going to change because it's always going to be 2. X equals 2 is fixed. Then you go ahead and plot these 2 points, and there's your graph. And of course, you're going to end up with a vertical line. Notice these equations of the form x equals some constant, they're always going to give you a vertical line. But please don't just memorize that, try to understand it. And a similar thing happens here, but this time it's the y value that's fixed, right? That doesn't change. So in this case, if you want to use points, basically go ahead and give x a couple of different values, because x can change. It's the y that is fixed, right? So then go ahead and plot those points and you're done. Now, one way of thinking about this is when they say graph x equals 2, they mean graph all the points in the plane. We're no longer on just a number line, right? If you're on the number line and they say go ahead and graph x equals 2, that's easy. You just go, there's 0, 1, 2, there is 2, right? But here, when they say graph x equals 2 in two-dimensional space, they mean all the points whose x value is 2. Think about it. For this vertical line, no matter what point you pick, there's one thing for sure: the x coordinate is going to be 2. And the same goes here. Here, when they say graph y equals 2, we mean graph all the points in the plane whose y value is 2. And notice, every point on this horizontal line will have a y coordinate which is 2. So if you graph the entire line, you have captured all the points in the plane for which the y coordinate is 2. If you only marked that point, you only marked one such point. Here, if you only mark this point, you've only found one point in the plane where the x value is 2. You have to make sure you catch all of them. That's why you get a vertical line here and a horizontal line here. Alright, so when we look at this, we realize, okay, this is one where one of the constants is 0 because we only have one variable term. So we go ahead and solve that for x. So we get 4x equals 12, divide both sides by 4, so we get x equals 3. So remember, this is one of those where the x value is fixed. So if you start at x equals 3, you're going to get a vertical line which goes through x equals 3. Well, which goes through basically, let me change my tool here, which goes through the point 3, 0. Like that. Again, if you want to use points, what is fixed and doesn't change is the x value. So you can pick a couple of points whose x value is 3. Y can be whatever you want it to be. All right. So there is 2 points. You can plot those, 3, 0 and 3, 1, and you can do it that way. Okay. That's all there is to that. Now, this linear form that we have learned about, the standard linear form, is a really good form for categorization, but it is not the most useful linear form. It doesn't give us a lot of useful information about the line. We know a little bit. We know, for example, if certain values are 0, we get certain kinds of situations like horizontal, vertical, or lines, oblique lines going through the origin, etc. But to get a lot of information at a glance from a line, we're going to have to go to another form. That form is called the slope-intercept linear form. What we'll do first is derive it from scratch, and then we'll utilize it. The slope-intercept linear form is by far the most important of all linear forms. It is the one that instantly gives you all the information you need to intuitively grasp the shape of the line, and also enough information to quickly graph the line. Once we know the slope formula, then deriving the slope-intercept linear form is a very simple matter. All we have to do is consider this typical line which has y-intercept at 0b. That means on the y-axis, that's corresponding to b, and xy is just a general point on that line. And if we find the slope of this line using these 2 points, so this fixed point, the y-intercept, and this floating point, which could be any point on the line, we end up with m equals, remember, we can just think of this as x1, y1, and think of this point as x2, y2. So we end up with m equals y2 minus y1, which is y minus b in this case, over x2 minus x1, which is x minus 0. So we end up with m. I threw a 1 under it so we can see it as a fraction, because we're going to cross multiply in a minute. So we get m over 1 equals y minus b over x. So if we cross multiply in this proportion, we get y minus b equals mx, and just adding b to both sides, we end up with y equals mx plus b. So this is where the slope-intercept linear form comes from, and it's a really useful form that we're going to be utilizing heavily from this point forward. So please learn it well. Okay, so for this problem, we're going to go ahead and graph this particular linear equation using 2 methods. First, we're going to do the familiar plotting of points. Remember, we only need basically 2 points to graph the line accurately. And also, we're going to do it by interpreting the slope. So by plotting points, we're already familiar with this method, and if I just go ahead and, since remember, when the equation is solved for one of the variables, the easiest thing is to do is to give the other variable a couple of different values, and then evaluate for the variable that the equation is solved for. So in this case, I'll let x be 0. So that wipes this out. So you get 0 minus 2, which is negative 2. Now, if I go to 1, then I'm going to end up with a fraction, which is not disastrous or anything like that, but it's just better to avoid if easily possible to do so. And here it is very easy to do so because all we have to do is, instead of using 1, is use 3 as our next x value, because if we do, then the 3's will cancel out and we get 2 minus 2, which is 0. So we didn't plan on doing this using the intercept method. It just happened to turn out that way because of the way the numbers worked out. So because, as you know, this first one is the y-intercept. What's the big telling point here? That this is the y-intercept, the fact that x is 0, and this one is the x-intercept, and you can tell because y is 0. So, and as you can see on the graph, those are indeed the points of intersection of the graph with the x-axis and the y-axis. All right, and so we plot those and we get our graph. Very easy. We just draw the straight line that goes through those 2 points. So if we want to do it without making a table, that's very possible now that we understand the slope-intercept linear form, because remember, the slope-intercept form has all the information you need to graph a line without actually making a table, because right there you know that that's b, that's the y-coordinate of the y-intercept, and of course the x-coordinate of the y-intercept is always 0. So just by looking at this equation, we can tell that 0, negative 2 is one of the points on this line. In fact, it's the point where the line will cross the y-axis. Now, we know the slope. We know that the coefficient of x, when the equation is in the form of y equals mx plus b, which this one is, of course, that's a minus, but you know that we can always write 2/3 x minus 2 as in this manner. And you can see that it is in y equals mx plus b form. Here b is -2. But we don't need to do that because we realize that that is the case, and we can just use the fact without having to actually go through this formality. But the formality is valuable because it's making sure that you understand precisely what the process is that's underlying the reason we accept this to be in slope-intercept form. So we know that 2/3 is the slope of this line. Let's go back to the previous page for 1 second. Remember that when the slope of this particular line ended up being m, the equation ended up being y equals mx plus b. That means this coefficient of the x variable here is the slope of a line when the line is written in this slope-intercept format. So the slope is 2/3, which I can interpret in two ways. I can think of it as +2 over +3, or I can think of it as -2 over -3. Each one will give me a different kind of point, each of these interpretations. If I consider this interpretation, that means starting at 1 point on this line, and of course we already have 1 point on this line, which is the y-intercept. I could go up 2 units, stop, and then go right 3 units because of the +3, right? And I'll end up with another point on that line. We already knew that, but remember, this time we don't have the table, so we're just coming up with that afresh, as if we didn't know it was there already from the previous work, right? So that's one way I could have gotten a point on this graph, the second point that I need to draw the line. Or I could have used this interpretation, which means starting at 0, -2, I could have done this. Remember, that's the change in y on the top, that's the change in x on the bottom. So I could have gone down 2 and then left 3. See? And if I did that, I would end up with another point on the line. Of course, it would be a different point from that one, but nevertheless, the important thing is that it would be a point on that same line. So if I draw the line from that goes through this point and that point, it'll be the same line that I obtained when I drew the line that went through the y-intercept and 3, 0. So we have options, and we can use either of those two interpretations to obtain the graph. So make sure you get comfortable with this new method, because that's like the fastest, most efficient way to graph a line when it is in slope-intercept form. Remember, as you watch a video lecture like this, the ideal thing to do is, if you think you know how to handle a problem on your own, then stop the video, pause the video, go try it on your own, and then come to compare your answers. If you have no idea how to do a certain problem, it's okay to watch it, right? Watch, learn, and then once you've learned it, copy that same problem, put away the computer, turn it off, turn off the screen, see if you can go through all the steps on your own without getting any assistance. If you can do that, that means you've probably have a very good idea of what's going on, and you'll be able to handle more on your own once you start the homework. If you can't, you may want to watch the segment again to make sure that you've absorbed it before you proceed. Okay, if you notice, so far we've been mostly graphing linear equations, right? Now we want to go backwards. You've noticed that we kind of tend to do that a lot in mathematics, right? We go from point A to point B, and then once you get comfortable doing that, we're like, okay, that was nice, now we got more work to can you go from point B back to point A? In other words, we like processes that are reversible, right? So which is actually one of the strengths of mathematics, because this being able to go forward and backwards in processes is the reason why so many disciplines can use mathematics to accomplish what they need to accomplish. One other real advantage of mathematics is the fact that it uses both inductive and deductive types of reasoning. Inductive reasoning is reasoning from specific to general, which is the type of reasoning that science utilizes. And deductive reasoning is reasoning from general to specific. That actually is the type of reasoning most religions use, but mathematics actually uses both of those types of reasonings. Of course, not in a belief-based format such as religion, but when it comes to deductive reasoning, but in its own very unique manner. And that also gives it a type of strength that puts it kind of in a category of its own, and therefore other disciplines can rely on it as well. All right, now that we're finished with that little bit of tangent, let's continue. So we're now going to, rather than use an equation of a line to graph it, we're going to use certain pieces of information that's going to be given to us, or even a graph, and then go backward and find the equation of that line. When it comes to finding the equation of a line that is neither horizontal nor vertical, and that's important to remember because horizontal and vertical lines will require a different kind of technique, which we'll study later. But for the kind of line that is neither horizontal nor vertical, in other words, for an oblique line, that's what those kinds of lines are called. An oblique line is a line that is neither horizontal nor vertical. Then you only need to remember this simple fact. You only need two pieces of information to be able to find the equation. You need m, which is the slope, and you need b, which is the y coordinate of the y-intercept. All right. Now, this holds for all oblique lines, again, which means non-horizontal and non-vertical. It would be impossible to find an equation of an oblique line if you do not have enough information at least to find the slope and the y-intercept. Now, it would not be impossible to find it without, say, one of those using another technique, but there should always be enough information to get these two if you so decided. So you will always have enough information to find these if you're asked in a problem to find an equation of an oblique line, even though that information, in other words, may not be given to you on a silver platter, right? It may not be given to you directly. You may have to do some work and exert some effort to find them, but you can rest assured that there will be enough information to find them if you're asked to find the equation of a line. Of course, that is not horizontal or vertical, meaning an oblique line. All right, so here we want to find an equation of the line passing through the point 0, 3 with slope -4. Provide an answer in both standard and slope-intercept linear forms. Remember, we need two quantities, right? M and B. Do we have either one? Well, as it turns out, we're kind of in luck in this case, because here, when they give us this point, there is something that gives away the fact that this is the y-intercept. So can you think of what that is? If you said to yourself that it's because the x value is 0, you would be exactly correct. All right, and so that means the 3 is b, right? So we have b, which is 3. And do we know m? Yes, that's given. That's -4. So are we ready to write the equation of this line? Well, let's see. Y equals mx plus b. So now we're just going to substitute -4 for m, and we're going to substitute 3 for b. So we get y equals -4x plus 3 as the equation of this line. Now remember, this is the slope-intercept form. But we were also asked to find the standard form of the equation of that line. Remember, the standard form is ax plus by equals c. So it would be very easy to find here, because all we have to do is we have to go ahead and move the -4x to the other side, which means add 4x to both sides. So of course you know that if you change sides, you have to change signs. So we get 4x plus y equals 3, and that's of course because you're just adding the opposite to both sides. All right, and there is the standard form. That's the standard form. Okay, so very simple. Again, if you already knew how to do it, great. If you didn't, pause now, try to do it from scratch without looking at the answer, and then we'll proceed. All right, so here's a problem that sounds very similar to the previous one. In fact, almost identical, right? So what is different? Well, what is different is the fact that the point that they give you that goes through the that the line goes through is not the y-intercept this time. Why? Because there's the dead giveaway right here, because that's not 0. Remember, you want to know if the point that's given to you is the y-intercept. Just do a quick check. Is the x-coordinate 0? You're good to go. If the x-coordinate is not 0, you need to go to plan B and try to do another approach. So when it comes to m and b, which we need, which one is given? Do we have one at least? Yeah, we have the slope, right? We have m equals -4. So we are given 1 point, 2, 3, and we're given that the slope is -4, right? So now we have y equals mx plus b. Since this point 2, 3 is on the line, that means it satisfies the equation, correct? So that means if I plug in 3 for y and 2 for x, and of course I know that m is -4, right? So, and then 2, then that should be a satisfied equation, right? That should satisfy the original slope-intercept form. So now all I have to do is solve this equation for b. So I get 3 equals -8 plus b. So b equals 3 plus 8. So b equals 11. And now I have the pieces of information that I require to write the equation of the line. Remember, y equals mx plus b. So in this case, I'm going to get y equals -4x plus, instead of b, we can now put 11. All right. Remember, that's the slope-intercept form. So to get the standard form, which is also requested, all we do is we move the negative 4x to the left side. That becomes 4x plus y equals 11. And there we have the standard form. That's it. Very simple and very, very manageable. Just try to do it on your own and we'll proceed. Alright, so this time we're going to find an equation of the line passing through these 2 points. And we want the answer in both standard and slope-intercept forms. Notice that when it comes to M and B, we're not given either directly, right? Could this be B? No, because that's not 0. Could this be B? No, because that's not 0. So we don't have B. And notice that there's no mention of the slope here, right? We're not given the slope. So are we given nothing? Well, are we given at least one of them that we can find quickly? Well, let's see. We have 2 points, and of course we have our good friend m equals y2 minus y1 over x2 minus x1, right? So yes, we have m put in directly. Okay, so we're gonna go ahead and find m since we almost have it. Let's just go ahead and call this x1 y1, and let's go ahead and call this one x2 y2. Okay, so we're going to have y2, which is -2 in here, see? Minus y1, which is 6, over x2, which is 4, minus x1, which is -3. So I need to parenthesize that. You never want to put two mathematical symbols like that next to each other. It's just not very good practice. All right. If you're going to do that, it's possible, but you'll want to use the raised negative notation like so. So that's okay. But this you want to avoid, okay? Don't use that. This one is okay. The best, the most advanced is this. This is what you're going to be doing from this point forward in your math classes. So we really stop using the raised negative notation pretty much after pre-algebra. Okay, so so we're going to get -8 over, remember that here we're going to get a these two turn into a plus, so therefore we get over 7, and that's going to give us m. Alright, so now we have the slope. The only thing left for us to do, so we have this now, that's the only one that we have to worry about. And of course, we have plenty of information to get it, right? In fact, we have more than we need now, because we only need now 1 point and the slope to approach it like the previous problem we solved, right? So in this case, we can use either one of these two ordered pairs. Makes no difference which one you use, right? So I'll just go ahead and use the first one. So we will use x equals -3, y equals 6, and m equals -8, 7 in y equals mx plus b to find B. That's exactly what we're going to do, okay? So we're going to get y equals mx plus b. When you're going to be doing substitutions, it's always a great idea to write the original equation first before you make any substitutions. That way you know that you're going to do it correctly. So here y is 6, so we write 6. M is negative 8/7, and x is negative 3, and then plus b. All right, so 6 equals, that's going to be, there's no cross canceling possible, so we get 24/7 plus b. Now the fastest way to solve that particular equation is to just go ahead and get rid of the fraction, right? So let's do that. So we're going to multiply both sides by 7. That means because of distribution, each of those 3 terms has to get multiplied by 7, like so. So we end up with of course here the 7s will cancel out now, so we get 42 equals 24 plus, this is a common mistake, students forget to multiply the 7 by the b, so watch out for that. So we get 7b is equal to 42 minus 24, right? Maybe that's 18, but yeah, so just to be safe, use a calculator. So 7b equals 18. We don't mind minor arithmetic computations being done on the calculator, but you want to do everything that requires brain power by hand in this class. So all the thinking parts have to be done by hand. All right, so b equals 18/7, okay? And remember, we just moved 24 to the other side, it became negative 24, and 42 minus 24 is 18. All right, so we have our stars of the show now, right? Those two, m and b, right? So we get y equals mx plus b. So y equals negative 8/7 x. Now we're just using a general point xy. We're no longer using a specific point like we did in the case of finding b, right? Now we're just using a general x and y, a general point xy on the line, right? And then plus 18/7. Okay, so that right there is the slope-intercept form of the equation of the line we just found. Now to get the standard form, all we have to do is very similar to what we did before. Move the 8/7 x to negative 8/7 x to the other side, becomes positive, and then plus y equals 18/7. The only thing with the standard form is, even though standard form works with any real coefficients a, b, and c, what we usually like to do is to not have fractions in this position. So it just looks a lot nicer if we clear the fractions, and that's what we'll do. Otherwise this would not be incorrect, it would just not be as nice. All right, so to do so, we'll go ahead and multiply both sides of the equation by 7, and notice that we end up with 8x plus 7y equals 18. So that's a much nicer looking standard form. And that's it. That's all there is to it. So this one was a little bit more involved, but it wasn't difficult, right? If you know your formulas, if you know the basic rules, it's really a simple problem, right? So, but you have to, of course, know everything that's involved. And notice that we had neither m nor b. So, but we did realize that because we have 2 points, we can use our formula for slope to get the slope. Once we got the slope, we approach it like the previous problem, which was to use one of these specific points given. We could have used either one. So you may be wondering, how could using this one give you the same result? Try it. You'll see, because it's on the same line, so it should give us the same y-intercept, because it's not going to be some point on some other line which would give us a different y-intercept. So you're still going to get the same b, but for your own sake, do try that. Instead of using 3 for -3 for x, go ahead and use 4. Instead of using 6 for y, go ahead and use -2. Okay, and make sure that you end up with the same b, and you'll see that you will. So, which is a nice thing. So use either of those 2 points and the slope to get b, and that's it. We're done. So we write the equation in slope-intercept form very quickly once we have that, the b, and then we just go ahead and convert it to standard form as well, because they asked us to give the answer in both forms. All right, so make sure that you can run through that without a glitch, without looking, and completely on your own before you proceed. Even though the slope-intercept form is completely sufficient as far as helping us find the equation of any oblique line, there is nevertheless one form of particular interest to us, because it actually helps us find the equation of a line when we have 2 points without having to find the y-intercept, which is what makes it a little bit interesting. In fact, that's the real strength of this particular form. Okay, so and it's not as universally popular or applicable as the slope-intercept form, although it could theoretically get the same thing done. We prefer the slope-intercept form just because it not only helps us find the equation efficiently, but it also is very powerful in allowing us to be able to graph a linear equation just by looking at it, basically. So the point slope form is not quite as powerful in that sense, but here we go. So let's go ahead and firstly go ahead and derive it from scratch like we did with the slope-intercept form. So if you recall, when we were trying to find the slope-intercept form, we used a fixed point which was not there, but it was exactly at the point of intersection with the y-axis, or in other words, the y-intercept. So this time we just still use a fixed point, but we won't use the y-intercept. We'll use some point other than the y-intercept, right? We'll just call it x1, y1, and then we consider a floating point, right? That means a general point on this line, so it could be anywhere on that line, right? And we obviously want it to be different from that, because we want to be able to write a proper slope formula so that these two don't become the same and give us 0 down here. So xy is any other point on this line, but x1 y1 is this specific point, right? It's a fixed point. All right, so if we find the slope of this line using the slope formula, just go ahead and call this one, just leave it as x1 y1, and this one we can call it x2 y2, right? So now watch what we get. We get y2 minus y1. So in this case, remember y2 corresponds to what we're just calling y. So we get y minus y1 over x2, which is just x, minus x1, which is just x1 itself. Okay, now again we're going to throw a 1 down here and we're going to cross multiply. So we get what? We get y minus y1 times 1, which is just y minus y1, equals m times x minus x1. And that is it. You can stop. That is the point slope linear form. All right, and you can use it to find the equation of a line, but remember that one strength that it has over any other form is the fact that you can find the equation of the line without having to find the y-intercept. And that's it. Okay, so here is a problem that should look familiar to you, because we did find the equation of the line passing through these 2 points a few minutes ago, but we found it using the slope-intercept method. So this time we're going to find the equation of the line that goes through these 2 points using the point slope form of the linear equations that we are studying. Now, we know that the point slope form is y minus y1 equals m times x minus x1. xy is of course a general point on the line. x1 y1 is a fixed point. Now we actually happen to have 2 fixed points, so we have more than enough, right? But we do need to find the slope first, so that's what we'll start with. So let's go ahead and call this one x1 y1, and let's go ahead and call this one x2 y2. So you get m equals y2 minus y1 over x2 minus x1. I always try to get you into the practice of writing the formula down first in its general form before you start plugging things in, because that reduces the chances of making a mistake. So now y2, which is -2, minus y1, which is 6, over x2, which is 4, minus x1, which is -3. Again, this should look familiar. We have found this before. So that's -8 over, and remember these two turned into positive, so 8 over 7. So now we're ready to write the point slope form of the equation of this line. So we get y minus, remember we could use either of these 2 ordered pairs as x1 y1, but since we went ahead and called this one x1 y1 where we were finding the slope, let's go ahead and use that. So y minus 6 equals the slope, which is -8, 7 times x minus x1, which is -3. So we get y minus 6 equals -8, 7th x. Actually, let's do one more step. That's going to become x plus 3. Now we're going to go ahead and put this in. This is we're finished as far as finding some equation of this line, but that's not usually a form that's very helpful to us. We either like to put it in point slope form, slope-intercept form, or standard form. So to do so, one of the things we're going to do is go ahead and get rid of this fraction really quickly. So let's go ahead and multiply both sides by 7. And remember, we can do so quite effectively like this. Remember, it has to be multiplied by each term, and of course all of this on the right side is just one term, so that only gets hit once, right? So notice that this 7 will cancel that one, so now we end up with 7y minus 42 equals negative 8x minus 24. So we can go to either one of those two forms first, makes no difference. Looks like it'll be easier to get the the standard form first, so we will go ahead and move the negative 8x to the other side. So we get 8x plus 7y equals, and we'll move the negative 42 to the right side to make it positive, so we get negative 24 plus 42, which is 18. If you remember, it's the exact same result that we obtained last time for the point slope form. Let me show you that real quickly. So here's where we solved the other approach, using the other approach with the slope-intercept, and see, we got the same result. Of course, it's not surprising, just wanted to make sure you see that. All right, so back to where we were. The only thing left for us to do now is to go ahead and take this equation and put it in slope-intercept form, because this time we obtained the standard form first, whereas last time we obtained the slope-intercept form first and then put it in standard form. So this is easy as well. What we'll do is we're just going toward this goal. The goal is y so y equals mx plus b. So we're going to go ahead and solve for y. So we get 7y equals negative 8x plus 18. So we just need to divide both sides by 7 now. So we end up with y equals negative 8/7 x plus 18 over 7. And there we have the slope-intercept form. All right, so we can see how to do this using both methods now. They're both fine. You know, the slope-intercept method is of course the method of choice, but this is nice to have in your arsenal. Also, if for no other reason, because it just gives you some really nice algebraic practice. There are two kinds of line relationships that have some interesting slope relationships that go along with them. One is the case of parallel lines, which, as you can probably intuitively guess, have equal slopes. And one is the case of perpendicular lines, which have negative reciprocal slopes. In more advanced algebra classes, you'll see proofs of these. They're not that difficult, but for the time being, we're going to accept them on faith and use them. So one way of showing that the slopes of perpendicular lines are negative reciprocals is to actually cross multiply this equation by actually using a 1 below the m1. If you cross multiply, you get m1 times m2 equals negative 1. So that's a nice way of remembering that as well, that if you have lines that are perpendicular, their product of their slopes is negative 1. All right, so now we want to go ahead and look at finding the equation of a line that passes through a given point 2, 5. And we're going to do two things. One, we're going to find the equation of a line that goes through the point 2, 5 and is parallel to this other line, right? 2x plus 3y equals 6. And then we're going to find an equation passing through the same point that's perpendicular to that same line that we had over here. Okay, so even though you don't have to graph these problems to get the answer, I think it's very important to have an intuitive grasp of what it is that you're actually doing, so that you're not just going through motions. You see, you're actually understanding what you're doing. So that's why I wanted to have these graphs here for you to get in touch with. Now, the actual procedure though is not going to require the graph, as you will see. Now, because I'm looking for the equation of a line that passes through this point, I know that I need M and I need B, right? So therefore, I notice that I don't have M directly for this problem, but I have a line that's parallel to the line that whose equation I'm looking for. And I know parallel lines have the same slope. So if I can find the slope of this line, I can also have the slope of the line that I'm looking for. So I'm going to find the fastest way for me to find the slope of this line is to put this equation into slope-intercept form. So I get 3y equals negative 2x plus 6. So we divide everything by 3 now. So we get y equals negative 2/3 x plus 6 divided by 3, which is 2. So I know that the slope is negative 2/3, correct? Now I'm just going to use this slope and that point. So I'm going to plug into y equals mx plus b. So I get, now for y we're going to use 5. For m we're going to use negative 2/3. For x we'll use 2 plus b. Okay, so now we just need to find b. So we get 5 equals, now if you notice my handwriting has deteriorated. It's not because I had a drink or anything like that. It's because I stopped writing on my tablet, because as you probably have noticed, I've noticed that there's a lot of distortion when I do that. So I'm writing on a external tablet, which of course the payoff is that my handwriting is going to get worse, because it's not as natural as writing directly on the computer screen. So there's always a payoff, right? So here we go, plus b. So now we're just, remember, the fastest way to solve this, get rid of the fractions. So we're going to go ahead and multiply both sides of this equation by 3, and of course you want to be careful to do it by each term because of distribution. So we end up with 15. I think my handwriting will adapt to this after a while, but it takes a while. So equals negative 4 plus, because remember these cancel out, the 3 and the 3. So negative 4 plus 3b. So we get 3b equals 15 plus 4, which is 19. So we get b is equal to 19 over 3. So now we have m and we have b. That means we are ready to write the equation of this line that we're looking for, because we know y equals mx plus b. So we're going to get y equals m, which is negative 2/3, x plus b, which is 19/3. All right, we're just going to take that and leave it in slope-intercept form. We already got enough practice by finding the standard form as well. So now notice that we're looking for the equation of the line now, which goes through this point and is perpendicular to that same line. So the only thing is, we know that perpendicular lines have negative reciprocal slopes. Now we're not going to go through this again because we already did here. The only thing is, this means the slope of the line that's perpendicular is going to be the negative reciprocal of that. The opposite of a negative number is positive, and the reciprocal of 2/3 is 3/2. So now we need to use this point and this slope to find the equation of this line that goes through the point and is perpendicular to that same line that we had over here as well. Okay, so we get y equals mx plus b. Remember, we're not going to repeat this part, we already did, so we're just going from this point forward. So y, which is 5, slope this time is 3/2, x is 2 right there, plus b. So we get 5 equals, notice that these 2's will cancel this time, so which makes it easier for us. We won't have to clear fractions this time. So we get 3 plus b. So b is going to be 2. So we get, now we're ready to write the equation of that line. So we're going to get y equals 3/2 x plus 2. And that right there is the equation of this line. Now here it's given to us by this fantastic program I was using, GeoGebra in standard form, of course. But if you take this and put it in standard form, you'll get what was provided there. Just to, you know, satisfy you for that's the truth of that. Here we go. Look, move this to the left side, multiply both sides by 2, so negative 3x plus 2y equals 4. Now of course, you know, usually we don't want a negative lead, so usually we'll multiply this by -1 to get 3x minus 2y equals -4. Okay, because we want the lead coefficient usually to be positive and whole. All right, so that's basically how you handle problems like this. Good ones, not very difficult. Make sure you can do them on your own before you proceed. If you remember, I mentioned the fact that all the techniques that we have discussed so far, whether it's using the slope-intercept form or the point-slope form, is really they're all really effective for oblique lines, which are neither horizontal nor vertical. How do we deal with horizontal and vertical lines? Well, with some reasoning and a really good understanding of the Cartesian coordinate system. Okay, so here we're looking for the equation of a vertical line that passes through 2, 7. So if the best way to deal with these is to go ahead and get a graph going. So here's the point 2, 7. We know we start here, we go 2 to the right, and then we go up 7, and we stop. All right, so for some reason my pen doesn't want to work. Let me try that again. All right, let's try this one more time. 2, 7. All right, so and we know that the line is vertical, right? So that's the easy part. So there we have a graphic of the situation we're dealing with. We have a vertical line that goes through this point, which is of course the point 2, 7, right? So remember, what can you tell me about every point on this vertical line? There's something you should be able to tell me about either the x value or the y value of any point that I pick. Let's say I pick this point. All right, not even a, let's not even pick a grid point. Let's pick that point, right? You may not be able to tell me much about the y value, right? And if I pick another one, you should be able to tell me, however, something about their x coordinates, right? They're all going to be what? They're all going to be 2, right? So, and remember, these vary and they could be whatever, right? We don't care, because the x value of the points on this line does not depend on the y value. It's always fixed, and it's what? It's 2. That's how you know the equation of this line is x equals 2. Just like that. So this is what I meant when I said you have to have a solid understanding of the Cartesian coordinate system, and you'll be able to come up with the equations for these very easily. So the recommendation is to plot the situation, and then the answer will pop right at you. It's very simple. Notice that for this one, we're dealing with a very similar situation and the exact same point, but this time we're looking for a horizontal line that passes through the point. So this time the sketch is going to look more like this. Okay, so again, we know what this point is. That's the point 2, 7, right? Now this time, what can you tell me? I'm going to put a few points, not even perfect grid points. Some of them will be. So those points, what can you tell me about those points? Is there anything that is consistently true about all of those points, right? And what is it? Well, this time, remember, it's not the x value. The x value changes. This time, what's fixed is this y value, right? For all of them, the y value is going to be 7. And that's precisely why the equation of this line is the equation of all the points in the plane whose y value is 7, which is exactly y equals 7. Notice that the y value of the points on this line does not depend on the x value. It's fixed and it's always 7. That's how you find that. Here we're going to find the equation of a couple of lines that are usually taken for granted and ignored, and they're two of the most important lines, right? One of them is the x-axis. Look, when you say that to people, they go, whoa, how do I find that? Well, remember, the x-axis is first and foremost just a line, right? Now, what kind of a line is it? Well, it's a horizontal line, right? And what value is it on it that does not change? Is it the x value or is it the y value? Remember, it's always the y value. The x value, of course, changes for different points on the x-axis, right? But remember, they're all at elevation 0, right? So their y value is fixed. So therefore, all of these points, if we were to put them as ordered pairs, would have the form, for example, this would be the point -7, 0. This one would be 7, 0. This one here is 2, 0. So you see it, they all have the same y value and it's 0. So what's the equation of the y-axis? I mean the x-axis? Y. For some reason it's not writing. Let's see, let's try that again. Alright, so y equals 0 right there. That's the equation of the x-axis. The equation of the y-axis, right, which is right here, is going to be different because for the y-axis, the y values obviously change. One thing that doesn't change is, for example, the x value. It's going to be always 0, etc. There's just two examples for you, right? So here we get x equals 0. All right, that's that. So remember, for these horizontal and vertical lines, you need common sense and you need a solid knowledge of the Cartesian coordinate system. For this next problem, we're going to find an equation of the line passing through the point 1/2, 2/3, which has undefined slope. So remember that the first thing we're going to try to do is do a sketch of the situation provided, and 1/2, 2/3 will be a point probably right around here, correct? So 1/2 in the x direction, 2/3 of the way in the y direction. So there's our point. So the only other piece of information they're giving us is the fact that it has undefined slope. So remember, the only kinds of lines that have undefined slope are vertical lines. So therefore, what we are dealing with here is this kind of a line. It's a vertical line that passes through the point 1/2, 2/3. So remember that all points on that vertical line are going to share some value. Which one is it? Is it the x value that's going to be the same for all of them, or is it the y value that's going to be the same for all the points on this line? Think about it, then come back to the video. Okay, so I'm hoping that you realized it would be the x value, right? Notice if I pick like that point, for example, what would be the coordinates of that point? That would be 1/2, 3, right? What if we pick this one? What are the coordinates? 1/2, -2. You see? The y coordinate here changes, right? See? But the x coordinate stays fixed. That's why the equation of this line is x equals 1/2. All right? So now here's what I would like you to do. I would like you to, I'm going to change the problem a little bit, okay? So I'm going to leave the first part as it is, right? Find an equation of the line passing through that point. This is the part I'm going to change, which has 0 slope. Okay, what do you think that line will look like? And what do you think its equation will be? Think about that for a minute, then come back to the video. All right, so you know that the only lines that have zero slope are horizontal lines, right? So that horizontal line is going to go through like this right here, right? But for the point that's on the line, not up there, but actually right here. So let's go ahead and draw it. So we know we're going to have a horizontal line going through right there. Just like that. All right, so for that horizontal line, we know that the value that is not going to change, obviously it's not the x value that changes, right? It's the y value that's fixed, right? So what is this y value right here? Think about it. Y value right here is obviously the y coordinate of this point, so it's 2/3. And remember, all the points here, for example, this point here will have what coordinates? Think about it. Remember, to really learn, keep pausing the video, figuring things on your own, and then continue. That's the trick. I'm giving you the real secret of learning mathematics. So please use it. So this point right here will have coordinates. Well, obviously the x coordinate is 4, and I'm sure you wrote the correct answer here. What do you think it is? You guessed it. Okay, the y coordinate doesn't change. So this point here, for example, would be what? Would be -2, 2/3, etc. So because of all that, the equation of, so what we found here was the equation of this line, right? X equals 1/2. So the equation of this red one is going to be y equals 2/3. Okay, so these are a couple of special ways in which they will define these lines for you, and you need to be familiar with that kind of language when you encounter it. So make sure you absorb that before we move on. And we are going to wrap this video up with graphing linear inequalities. Graphing these inequalities is quite simple if you know how to graph lines in slope-intercept form, which we've already discussed. So for each of these, we're going to be graphing what is called the boundary line first, which is simply the inequality where each of these inequality symbols is replaced with an equal sign. And that is the boundary line that we're talking about here. In fact, for each of them, the boundary line is the line y equals 2x plus 3, which we've already seen and we know how to handle. So we can say for each of them, the boundary line is the line y equals 2x plus 3. The reason we're doing all 4 of these graphs together is because the initial part of graphing all of them is exactly the same. We determine the boundary line, which is basically the equation that replaces the inequality symbol with an equal symbol, and then we can take it from there. Now let's go ahead and do so, but before we do, it's important to note that, for example, when you have a strict inequality such as the first case and the third case, then you're going to want to draw a dashed boundary line, given that the boundary line itself will not be part of the solution set, because That's what strict inequality means. On the line itself, we know that the y values are exactly equal to 2 times the x value plus 3 for any ordered pair xy, right, on the line. However, if we're looking for all the points in the plane whose y value is greater than that quantity, we're going to want to draw all the points above that line, right? So the line itself will not be part of the solution set that will be satisfied by that inequality. Now, so for this case, the first case and the third case here, we're going to be graphing dashed or dotted lines, and for these two we'll be graphing solid boundary lines. So we are going to be graphing the same line, so the analysis is the same. We'll do that up here. So notice that for all 4 of those boundary lines, which are the same boundary line basically, the y-intercept is 0, 3, and the slope is 2, which we can of course write as either positive 2 over positive 1 or negative 2 over negative 1. So starting at this point, we can either go up 2 and then right 1 to get another point, or we can go down 2 and then left 1 to get another point on the line. It makes no difference. So let's go ahead and start at 0, 3. So there's 0, 1, 2, 3. All right, so we can go up 2, right 1. So there's up 2, right 1. Put a point there. Remember, we're going to be drawing a dotted line. So we go ahead and do so. There we go. Okay, so now we're going to graph this one as well. So the exact same line, and also the exact same dotted status, right? So go up 2 over 1. So now we do the boundary line. All right, so we're also going to do these two, but remember, for these two, it says less than or equal to. In other words, the places where y equals 2x plus 3, in other words, on the line itself, those satisfy this inequality as well as this one. So the line will be part of the solution set for those two cases, right? So we have the same 2 points will work. So up to right 1. So 0, 3. By the way, down to left 1 will give you the same line. So let's do that one just for variety. All right, now we're going to go ahead and draw the lines, but this time we're going to draw them solid. So, and then over here we're going to do the same thing. So I better be okay. So you see, the initial part of graphing each of these 4 inequalities is the same, except for the fact that strict inequalities are going to require you not to include the boundary line. Remember, for each of these 4 inequality, this line is called the boundary line. So why is it called the boundary line? Because it's the boundary between the zone that will be a solution set for this inequality and the zone which will not be part of the solution set. So in this particular case, we're looking for all the points in the plane whose y value is greater than 2x plus 3. So we're going to be shading above, because remember, on this line, the y value is exactly 2x plus 3. So where are the points whose y value would be more than that? Well, they would have to be above, right? Above this line. So we're going to shade above this line. Okay, so here we have shown the shading above this line. So this is the region that we call the solution region for this inequality. For this one, remember, it's going to be pretty much exactly the same, except the line itself, because it says greater than or equal to. So the case where y equals 2x plus 3 is also included in the solution set. So it's going to look almost exactly the same, except we'll be shading above that line and include the line itself. All right, so it'll look something like this. So for this one, notice that we're looking for the points in the plane whose y value is less than 2x plus 3. We know that on the line itself, on the boundary line, the y value is exactly equal to 2x plus 3. So if we're looking for the points in the plane whose y coordinate is less than twice the x coordinate plus 3, we would be looking below that line. So that's exactly where we're going to be shading. And for this last one, of course, it's going to look almost exactly like this, except that because of the less than or equal to sign, instead of the less than, we're going to be including the line itself. All right, to sum it all up, notice that all four of these inequalities have the same boundary line, basically. The difference being that with strict inequalities, the boundary line is not included as part of the graph of the solution set of the inequality. With the boundary lines that are in the form of greater than or equal to or less than or equal to, because the equal case is included, that means the line itself is included in the solution set. So when we're looking at inequalities involving greater than, which is these two, we're going to be shading either only above or on or above the boundary line, right? So in this case, we only shade above the boundary line. In this case, we shade on and above the boundary line. For these two, which involve less than, we're going to be shading below. Remember, we're looking for y values that are less than the y values on this line, right? So those would be below this line. And in this case, we only shade below, we don't include the line. And in this case, we shade below the line and include the line. So these inequalities, as I said, are very simple to handle if you have them in the correct form, which is the slope-intercept form, because then you just have to figure out, you know, the dashed or solid status, and also whether you're going to shade above or below. Okay, so here we have some inequalities, but they are not in slope-intercept form. So we have a little bit of work cut out for us. We're going to first put each of them into slope-intercept form. It's going to be very quick and very easy, but we need to take care of that. So we have 3y, we'll keep that on the left side, greater than. We'll move the 2x to the right side, it'll become negative 2x plus 6. And then we have y greater than. This time we're going to move the 3 out of the way, so we're dividing both sides by 3. So we have greater than negative 2/3 x plus 2. Notice that the steps involved for this one would be exactly the same, right? The only thing that would change is this would become greater than or equal to. So this one would be y is greater than or equal to negative 2/3 x plus 2. And similar here actually, except here we're going to get y less than negative 2/3 x plus 2. And for this one, we'll end up with y is less than or equal to negative 2/3 x plus 2. So again, notice that we're going to be trying to graph the boundary line, and when we do so, we have to be careful about whether we need to draw it solid or dashed, right? In other words, whether the boundary line is going to be included or not. Notice that for this one, the boundary line will not be included, nor will it for this one, because these two are strict inequalities. For these two, the boundary line will be included. So I think I'm going to get this graphed using a graphing software right now, because it'll do so much a better job than I will by hand. However, we did the last one manually, so that precisely the same steps will be involved. In other words, we're going to start at 0, 2, then we're going to follow the guidance of, so notice that for all of them, the y-intercept is 0, 2, and the slope is negative 2/3, which we can write as positive 2 over negative 3 or negative 2 over positive 3. So starting at 0, 2, we can either go up 2, let's say that's 0, 2, we can go up 2 and then left 3, to get another point, or we could go down 2 and then right 3 to get another point. Notice they're all going to line up anyway. So these 3 points all line up and we have our line there. So now I'll go ahead and graph this now that we know what we're doing. That's going to be the boundary line. And for this one, we'll shade above. For this one, we'll shade on or above. This one will shade below the boundary line, for this one on or below. So let's take a look at that together. Okay, so note that for each of the graphs, we have the same boundary line, right? And for the first and the third ones, we have the boundary line in dashed form because it's not part of the solution set for the inequality. In the second and fourth one, we do have solid boundary lines because the boundary lines are part of the solution set. And we can also see that in the greater than and greater than or equal to case, we shade above, right? Of course, with the greater than case, only above. With the greater than or equal to case, we shade above and the line itself. Now, when we say shade, of course, we mean we include the line. For the less than case, we shade below. If it's strict inequality, dashed or dotted. If it's less than or equal to, then on or below the line. So very, very simple. That's how you graph these linear inequalities. All right, so we're going to go ahead and close today's lesson with two special cases. Here we want to graph x greater than or equal to 2. So you have to be very careful with something like this because normally when we're dealing with just the number line, you know, we would basically put a 2 on the number line. And go ahead and make a closed circle and then shade to the right, correct? But remember, we're in the plane now, so we're dealing with 2 dimensions. So when we say graph x greater than or equal to 2, we mean all the points in the plane whose x coordinate is greater than or equal to 2. And if you think about it, that would be everything that you see shaded here. Now, you know that the boundary line here would be x equals 2 itself. So it's that vertical line. Remember, the graph of x equals 2 is a vertical line. Now, because it says greater than or equal to, it's a solid line because it's included in the graph, right? And because it says greater than, basically you're going to shade to the right. So in other words, pick any point in here, right? You know it's going to have a x coordinate which is going to be greater than 2, right? Y coordinate could be any value. It could be very small in the negative range, it could be very large. But one thing is for sure, the only thing you can say for sure about everything that you see shaded here and the line itself is that its x value, its x coordinate, remember every point is composed of ordered pairs xy, right? One thing is for sure, any point you pick in the shaded region or on the line, its x coordinate is going to be greater than or equal to 2. That's all there is to that one. For this one, notice the boundary line will be this horizontal line, y equals 2. Now we know that the graph of y equals 2 is just a horizontal line, right? But what if we want all the points in the plane whose y value is greater than or equal to 2? If you think about it, that would be everything that you see shaded. If you pick any point in this shaded area, it doesn't have to be a perfect corner point either, any point, right? One thing you know for sure is that its y coordinate, meaning the y value, is going to be greater than or equal to 2 because it's above this line at 2, right? The x value could be anywhere, right? The x could be here, the x could come from the left, the right, etc. But the y value, we can say something about for sure that it's going to be greater than or equal to 2. And again, because it says greater than or equal to, you include the line itself. If this one were x greater than 2 instead of x greater than or equal to 2, it would look exactly the same except the line here would be dashed. And for this one, you would have the exact same graph if this were y greater than 2 instead of y greater than or equal to 2. Everything would look the same except the line would be dashed. All right, so there's a review of graphing linear equations and inequalities, which brings to a close our review of basic skills mathematics to kind of compensate for the fact that there's no longer elementary algebra offered at most colleges around the country. So therefore, I hope that's helpful for you and will prepare you well for your journey into algebra and beyond.